So after hectic session, now the time has come when we should relax and try to see what we have been discussing all through. So what I decided today, let me go through quickly whatever we have done so far. If you see, we started with definition of static stability. Now, when you are discussing about static stability, we have very well understood that it is the initial tendency of the body to come back to its equilibrium while it is disturbed from the equilibrium, right? So, for aircraft, we were discussing about longitudinal stability. We have discussed about lateral stability. We have discussed about, or let me write like this, we have in a sequence we have done directional first, directional stability, then we have lateral stability. All are static stability, right? Let me write here stability. That makes things look better. Now ask ourselves a question. What was the condition for longitudinal static stability? We know that from our CM versus alpha graph, we know that if the aircraft has to be stable at alpha trim, which is here, where CM is 0, then the condition was dCm by d alpha less than 0. Similarly, for directional stability, we realized if an airplane is going straight like this, and because of crosswind there is a beta introduced, so the airplane should have initial tendency to nullify that, so it will turn the airplane or generate a yawing moment positive. So we said C and beta greater than 0. And for lateral stability, what we understood was the airplane is going like this. If because of some disturbance it has banked like this, so if it is laterally statically stable, it should generate a moment which will produce a negative moment. Disturbance is like this, so it should generate negative CL, negative rolling moment, right? And how that mechanism was generated, or how this mechanism works, it is as the airplane banks, it starts side slipping, and as side slips, there is a vertical tail primary, so that gives the rolling moment. Of course, you can get it from the wing also, a little bit. So the condition was for a positive beta, it should generate negative rolling moment. That is, if there is a bank like this, it induces positive beta, and if it has to come back, then it has to generate negative CL, because CL is positive right wing going down. Okay, so we say CL beta should be less than 0. And who are the main contributor towards these conditions? If you see for CM alpha, it is the horizontal tail, main contributor. Okay, please understand the key word is main contributor. Then for CN beta, it was vertical tail, and for CL beta also you have seen it is vertical tail, and also we have seen that high wing, okay, and also we have seen if I give some dihedral to the wing, right? High wing, you understand, high wing is this, the wing is here, and dihedral you understand that I am giving some angle like this, and this angle is, let's say, gamma, a dihedral angle. So you understand what are the conditions? You also understand who are the main contributor. When I say dCm by d alpha less than 0, the main contributor for stability or static stability is horizontal tail. Wing also contributes towards stability. If the aerodynamic center of the wing is ahead of CG of the airplane, it is destabilizing. If it is aft of CG, you know it is stabilizing. And similarly for fuselage here, it is mostly destabilizing. And CN beta also you get from fuselage, which is also again destabilizing. but vertical tail, it makes it stabilizing, right? Wing also, if we give a sweep, it will have stabilizing effect. If I summarize this, I write Cm alpha because of wing, Cm alpha because of fuselage, Cm alpha because of horizontal tail. So if we see these three derivatives, one thing I can take guarantee that this will be less than 0. This will be always stabilizing. As far as fuselage is concerned, you can very well see fuselage typical shape is like this, and its center of pressure will be somewhere here, and CG will be somewhere here, so it is always destabilizing. Or I can write Cm alpha greater than 0, and for wing, we know if AC of the wing is behind CG of the airplane, then dCm by d alpha is less than 0, or wing contribution is stabilizing. If AC of the wing is ahead of CG, it is destabilizing. So it could be either less than 0, it could be either greater than 0, depending upon where is the AC location in relation to the center of gravity of the airplane. No issues about this? Okay. Now, coming back to the vertical tail, or Cn beta. What was Cn? Say Cn beta, right? What was Cn? Cn was yawing moment, non-dimensionalized by half rho v square s into b. B is the span. And what we have seen for directional stability, Cn beta should be greater than 0, or if I plot Cn versus beta, the slope will be like this, and this is dCn by d beta should be greater than 0. You could see from here, beta equal to 0 is the trim, because we want to fly at beta equal to 0 almost all the time, except one or two occasions during landing, or sometime you want to reduce speed by increasing the drag, you go like this. But take it for understanding that we want to fly at beta 0. Nobody will like to fly like this. We want to fly like this. So if from here you could see, if by disturbance beta positive is introduced, it will automatically generate a yawing moment positive. And what is yawing moment positive? It is the right wing going back. So this will make the beta to come back to beta equal to 0. So it will have initial tendency to come back to 0. So this is the understanding of directional stability. And again, you should know that directional stability contributors are Cn beta wing, then Cn beta fuselage, and Cn beta vertical tail. Right. So once I have seen this vertical tail, if I put vertical tail, I can guarantee that Cn beta will be greater than 0. That is, if I put a vertical tail on a fuselage, whether this way or whether I put the vertical tail like this, in both the case, Cn beta will be greater than 0. Please, there are two different configurations. Right? Okay. Sometimes you put the vertical tail up, sometimes you can put vertical tail down. Whatever this combination is, Cn beta will be always greater than 0. Right? Then you have Cn beta fuselage. Based on this understanding, if there is a beta, then you could see here, if there is a positive beta, this will give a force in this direction, and that will give a moment which will take left wing backward. That is, if I am moving like this, force is here, that will take the left wing towards back, and Cn beta is less than 0, so this fuselage, Cn beta is less than 0, it is destabilizing. Because for directional stability, I want Cn beta to be greater than 0. For wing, we have seen, if I introduce sweep angle, then Cn beta, because of wing, is also greater than 0. It is stabilizing. And this is the interesting part. Many times you will find suddenly there was a hype that vertical tailless airplane, right? The airplane without a vertical tail, because there are some configurations which are for military purpose, you do not want to keep vertical surface because that increases the radar cross-section area, so that it can be traced by radar. So better to not to have a vertical tail, so that you are reducing the radar cross-sectional area, we call RCS, or radar cross-sectional surface. So people will tell, oh, this is a great job we are doing, there is no vertical tail. So directionally it will not be stable, because directional stability is given by vertical tail primarily. But you could see that if you give a sweep, you can get it from wing also. So nothing very big claim. You can get Cn beta positive, you can stabilize directionally by making the wing having a sweep. That is why vertical tailless airplane, whatever you might have seen, stealth aircraft, B-2 bomber type, there are no vertical tail. There are control surfaces here, somewhere here also something is there, right? It doesn't have a vertical tail, but it has a large sweep. And this sweep, we have demonstrated through expression, this sweep gives Cn beta greater than 0. So because of this sweep, you are now having directional stability in terms of static stability is concerned. So nothing to hype about it. There is no vertical tail, so how we will get a directional stability? Okay, right? So this was the discussion we had, and a lot of expressions are there. So what I have decided, in one of the forum, I will be also pasting those derivations step by step, so that you can do your homework, you can revisit those expressions and derive yourself. Right? Sometimes it becomes extremely difficult to continue deriving expression here in this sort of a mode of interaction, where I do not understand how much you are getting into it, right? Where to stress, where not to stress, especially on the derivation part. So in one of the blog you will find all the derivatives will be given, right? And you can ask questions based on those steps. Okay, this we have done, and why we have done all these things? That is the question. First of all, our final aim is to also check whether the airplane, whatever we are discussing about, are dynamically stable or not. That's why we started with static stability. Now we'll be stepping towards dynamic stability. And while we'll go in this process, we'll try to develop equation of motion. Okay? So what will be the philosophy? You have equation of motion, and then give a perturbation and see how the displacements are responding. If it is damping out, then you say it is dynamically stable. If it is going on increasing, you can say it is a dynamically unstable. So what are the steps required here? If I want to go for dynamic stability study, what I will do, first of all, will think of equations of motion. Just to give you an example, what is the meaning of equation of motion for a flight vehicle, I will take a simple example and try to share with you or create a roadmap for the final 6-degree of freedom equation of motion, equations of motion. So what we will do, let us take a simple example, right? Let's say a projectile of mass m is fired at an angle gamma, flight path angle. This is the velocity vector, and we want to write the equation of motion. That means we want to know how its position is changing, that is, and how is its velocity changing, speed changing. What we do, we fix some x, y, let's say I write it x, I write it y, is the coordinate system. I am thinking of, let's say, simple planar trajectory. That is, assuming that the projectile is fixed in the vertical plane. This example is just to illustrate you how to start thinking. Okay? When I want to write equation of motion, typically what this is called, we see we are actually trying to develop point mass equations of motion. When I say point mass, that means I can equivalently write this in this fashion. Right? As if the whole mass is concentrated at the CG of the projectile. There is an implicit assumption this is stable. Right? If it's not stable, then we will not be able to solve the way we are doing it. And now if I write it like this, I know what are the forces acting on this projectile. You know that there will be drag on the fin, drag on the body, drag everywhere, skin friction drag, pressure drag will come. So we are expert now. We know the total drag. I know how to compute, and from there I can find out what is the CD, drag coefficient. That is known. So the velocity direction, the drag will be in the opposite direction. And where will be the lift? Lift will be perpendicular to the velocity vector. And there will be weight here, mg. Correct? Now we'll make a further assumption. We'll say angle of attack, alpha, is almost 0, or we are neglecting the lift, which is in true case for this sort of a shell. When they are fired, their angle of attack is very, very small, 0.1 degree, 0.2 degree, because that is the angle at which it is in equilibrium. All are everything is symmetric, right? We have realized that. So we are neglecting this lift, so lift equal to 0. Now we want to write the equation of motion. So what I do, I choose two axes, one along V and one perpendicular to V. Right? Let me write the motion along V and one perpendicular to V. I can as well write the whole component along Y and X, but I am just giving you exercise. We are solving an exercise where I am writing equation of motion along V and perpendicular to. So what is the step I should follow? I know I should be very clear that I have to follow F equal to ma, force equal to mass into acceleration, and I should know that these are all in inertial frame. Now I want to write the equation of motion along V direction. So that will be what? M dV by dt equal to the net force. Why this is m dV by dt? Because actually it should be dV by dt of mv. This is m dV by dt plus v dm by dt. But we are assuming mass is constant. We are assuming mass is constant. See, this assumption will not be strictly true if it's an aircraft, because in aircraft, the fuel consumption will be there. This assumption will not be true for a rocket having solid propellant, because as time goes, the propellant mass gets consumed, so the weight reduces. This will be true strictly for a shell, like a Bofors shell, right? Where they are given initial kinetic energy. So there are no active propellant sitting inside, so mass will remain constant. So that is how I can take this as m dV by dt. So this is the acceleration generated. Who is causing this acceleration? There must be some force. What is the force? Force is, I'm writing along v direction, so force is minus drag and minus mg sine gamma. You could see from here, this is gamma, so this component is mg sine gamma. This is one. Now, what about when I write the equation along a direction perpendicular to v? So what is this equation will be? So here, what are the forces acting perpendicular to v? Is minus mg cos gamma. And what is this causing? This is causing, you could understand, any circular motion. This is v, and this is tension. So this tension is perpendicular to v. So what sort of acceleration you get? You get centripetal acceleration. This tension, which is perpendicular to v, will generate a centripetal acceleration. And you know centripetal acceleration is mv square upon r. Okay? Now you see, I can further write this as m v into v by r is equal to minus mg cos of gamma. What is r here? Mv square r. R is the radius, right? Because this force, whatever is there, mg cos gamma, right? It will try to turn the trajectory. So there will be radius of turn. So now, what is v by r? V by r is at what rate this velocity is turning, right? And since the angle of attack is say 0, so whatever the rate angle of attack is turning, by this assumption, it is the same rate at which your axis of the projectile is also turning. So we call it now mv into gamma dot, that is angular speed with which the velocity vector is turning, is equal to minus mg cos gamma. So you get gamma dot equal to minus g cos gamma by v. So what are the equation of motion we got when you wrote it like this? One is dv by dt is equal to minus half rho v square scd by m minus g sine gamma. I have divided this by m all through. And our second equation I got is d gamma by dt is equal to minus g cos gamma by v. What is our aim? We want to find this coordinate of this projectile in terms of x and y axis, right? We are assuming that it's a planar trajectory. So we have to add third equation, that is dx by dt is v cos gamma, and fourth equation is dy by dt equal to v sine gamma. Are clear? Because this is v and this angle is gamma, so this is v cos gamma and this is v sine gamma. What is v cos gamma? It is the rate at which the projectile distance is changing along x, that is v cos gamma, and v sine gamma is the rate at which the distance of the CG is changing along the y direction. Okay. So now you could see that these are the four very standard point mass equation of motion. How to solve it? Let us see. See, first of all, we identify these are set of differential equation, first order differential equation. Also, we see that equation number 2 and equation number 1, this gamma is present. Gamma is here, gamma is here. In here also gamma is here, here gamma is here. So you could see V is here, V is here. So you could see V is here. So you could see that they are coupled differential equation, first order differential equation, right? So to solve that, we need to have initial conditions, and let's set the initial condition. If I want to see these two equations, I need to write at t equal to 0, x equal to, let's say, x naught, and y equal to y naught. So it depends, this is decided by where from you are firing, where from you are launching it, right? So that reference will have some coordinate. Then also here you see in this at t equal to 0, what is v? V equal to v naught or v launch, right? And also you know this gamma at t equal to 0, gamma equal to gamma naught, or that is called launch angle, right? At what angle I am launching? 10 degrees, 20 degrees, 45 degrees, 55 degrees, to get different types of values of x. This value of x, value where it is falling like this is typically called as range. Right? And whatever in the y direction happening, it's x of course, yes. And along the y direction, you know, these are in the height of the trajectory. So you have a maximum height, you have a maximum range. I'm only talking about planar trajectories. In actual practice, you will find these are three-dimensional, so there will be drift also. It will have a distance covered along the lateral side also. So those things we will be now adding in 6DOF. In point mass, this is a fairly simplified way to write equations of motion, and you realize that these are first order differential equations, coupled first order differential equations, and you need to solve them by numerical methods. And you know that there are so many methods to solve these equations. If possible, we will be loading one or two software or code so that you can use it. But anyway, you can go to MATLAB and just solve this equation using standard routine. Okay. This lecture is given to you to make you understand simple point mass model when I am developing. What are the things I need to know first? First is, what is the axis system I am talking about? Then, what are the forces? Right? In all directions. And that is where a 6DOF concept comes into mind. And how do I do that? Although today I will not talk about 6DOF, just in warm up, you know what we are heading towards. You are familiar, this is the axis system, this is x, this is y, this is z. So I'll have force along x direction, I call it Fx, force along y, Fy, force along z, Fz, then moment about x, Mx, moment about y, My, and moment about z, Mz. Right? We know the convention that Mx is positive when right wing going down, which is rolling moment. My is positive when nose is pitching up, and Mz is positive when right wing is going back. I need to know how to calculate this Fx, Fy, Fz, Mx, My, Mz, so that I can write an equation of motion. Here, only drag force was required because we had a simplified assumption, point mass. So I needed to know what is the drag coefficient value, correct, to find the drag. But in the 6DOF, I need to know so many coefficients so that I can model Fx, then Fz, Fy, My, Mx, all such things. So that's how it becomes a little involved. Okay, not complicated. It gets involved. It's a question of matter of putting time. Nothing, you don't require any extra IQ for all these things, right? These have been done 50, 70 years back, 100 years back. So don't get nervous unnecessarily. Yes, you may not like these expressions. Doesn't matter. You may not like, but they are very useful. This neem toothpaste I never liked, but they are very useful. Okay, so please be clear. This needs attention. It is effort. Don't unnecessarily say it's complicated. Absolutely, today's youngsters should not find this complicated at all. Okay.